This first video is an introduction to the key ideas that underlie density functional theory. As a reminder, we're seeking the ground state for n interacting electrons. Though of course this is not something that can be done exactly, so we're going to want to find approximate ways of doing that. And these electrons are in an external field which is represented by the potential V of R. The Hamiltonian can be written as H is equal to T, the kinetic energy, plus U, the electron interactions, plus V, the external field, and we sometimes choose to write that as H0, in other words the terms involving only the electrons, plus V, and then the ground state energy, EGS, is given by the expectation value of the many-body wave function and the Hamiltonian, like this, where of course the wave function there has to be the ground state. Density functional theory offers an exact reformulation of this problem, which then allows approximations to be made and correct, and well, not correct because they're approximations, and approximations to be made to the ground state energy. It proves to be a scalable and not too expensive method, which is also accurate. So we're going to start by talking about the Hohenberg-Kohn theorems. These underlie density functional theory. So Hohenberg-Kohn theorem number one, it starts by thinking about the relationship between the system we're trying to solve and the external potential. It should be clear that the external potential, V of R, will determine the ground state, which will of course consist of the many-body wave function, which gives us the ground state energy and the resulting charge density. What we saw when we were dealing with Thomas Fermi theory was that actually we try and invert that, and we try and get some information about the, we try and specify the ground state itself in terms of the charge density, which then determines the properties of the system, and ultimately you could say that the charge density determines the potential V of R. So the first Hohenberg-Kohn theorem helps us to do this, and it is as follows. It is impossible for two potentials, V of R and V prime of R, which differ by more than a constant. Of course, if you just add a constant, then you're just shifting the energy zero, so that's a trivial solution, to give the same ground state charge density. Now, this result is proved in the notes, so I'm not going to do that here, but what we should stop and think about is what the implications of this are. What we're saying is, if you can only have one potential giving one ground state, then we could invert that map and we could say that, therefore, rho of R, the charge density, determines V of R. And hence, it determines the ground state, the energy, and the many-body wave function. There are some subtleties here. If you're interested in the very detailed maths, there's plenty that you could read about, but that's an incredibly important information, and it means that we can write the following. So we could write the ground state energy is equal to the integral dr of rho of R V of R. So that's the potential energy that comes from the interaction between the electrons and the nuclei, plus a functional f of rho of R. F, of course, represents the expectation value of the Hamiltonian, or H0 that is. F is equivalent to the expectation value of H0, so the kinetic energy plus the electron-electron interaction. And what we're saying from this first Hohenberg-Kohn theorem is that specifying the charge density ρ determines F and hence the ground state energy. The second Hohenberg-Kohn theorem relates to minimization and the variational theorem. So Hohenberg-Kohn 2. And what this says is that the ground state energy for a potential V of R is found by minimizing the functional, which we've just written above, with respect to rho, but also while for fixed electron number. Now this is very familiar. It's exactly what we were asserting for the Thomas Fermi theory, and again the result is proved in the notes, so I won't talk about it. But what it means is that we now have a way to find the ground state of an interacting system simply in terms of the charge density, and that simplifies life enormously. It means that we actually have a practical approach to solving for the many-body problem. Let's just consider the terms in the energy, because this is something that's very helpful, because you're going to need to know these terms in order to do the calculations. There we are. So the terms in the energy can be written as follows. We're going to express the functional F in terms of the kinetic energy, the Hartree energy, which is the electron-electron classical interaction, and then an extra term called the exchange correlation. So we're going to write that the ground state energy, EGS, is the integral dr, V of r, rho of r, plus EKE of rho of r, plus E Hartree of rho of r, plus EXC of rho of r. Here, XC stands for exchange and correlation. We've already seen the exchange term. Correlation is it's a term from quantum chemistry, which actually means it's defined as the difference between the Hartree-Fock energy and the correct many-body ground state energy. In other words, it's all the many-body quantum effects that we haven't included in Hartree-Fock theory. Let's define these. So the first term, the electron-nuclear interaction, that's an exact result. So that's fine. Let me put a 1 over the top there. The second term here, that's the kinetic energy. This is rather unusual. It's the kinetic energy, and it's defined very specifically as the kinetic energy of a non-interacting gas, a non-interacting electron gas, of non-interacting electrons. We'll see why that is in a minute, but it's quite important, and it's different from what you might expect. The third term, that's number 3 here, that's just the standard Hartree energy, and it's defined in the usual way. E Hartree is given by a half times the double integral dr prime of rho of r prime over 4 pi epsilon naught r minus r prime. The final term, which in many ways hides all of the dirty laundry of density functional theory, is defined simply as all the remaining terms of the energy we have not yet accounted for. Formally, that's an exact definition. However, we don't know what form it should take, and so we have to make approximations, and we'll touch on those at the end of the next video. So there's a basic introduction to the key ideas underlying density functional theory. It's an exact reformulation of the many-body problem. Notice that it works in terms of the charge density, so it's a much simpler way of approaching the solution. And also notice that there's a glaring problem, which is that we don't know the form of the exchange correlation energy functional, and so we're going to have to approximate that. In the next video, I will go into a little bit more of the details of how these calculations are done and how we find these different terms.